Okay, gang, I hope everybody's back. What we're going to do now is we're going to kind of concentrate on the procedures. We're going to first start talking and showing you how the crew used these, where they were, and that kind of thing. And then we're going to talk, we're going to look at what flight instruments did they use, and what controllers did they use, and that kind of thing. And then we're going to kind of step through just a couple of these just to give you an idea what some of them looked at or looked like. So as I mentioned earlier, the contingency boards card, for the most part, were two card sets. And over here is the contingency board. This is the nominal tile trajectories on the left and RTLS contingency board card on the right. Now, each card or each position in the cockpit had their own card. And there are three positions you worry about. The commander, who's actually doing the physical flying, the pilot, who's helping them with systems, and then the MS2, who's acting as the flight engineer, i.e. the guy cracking the whip and making sure everybody's trying to stay on tack. And so the nice thing too is if you look at over here, this is a card from a PLT, and actually I can look down here, and this is from STS-39, and you'll see that inside the cards on the actual procedure sets that they're highlighted yellow. And each card would have different, the commander and pilot's card would be different because they had different things to do. If it's the pilot's card and you see it's white, then the commander's doing it. And then vice versa if it's a commander's card. And the cards themselves is just, you can see 3 engine out at the top, 2 engine out in the bottom. That holds for both of these. And then at the top, we always had the regions color-coded. And that made it really easy for everybody to get on the same page quickly. For instance, 3 engine out blue is here for the contingency board card. If you're going straight ahead, that's what you have. So if somebody calls 3 out blue, everybody's right there right away. If you call out 3 out green, they're right here right away. Same thing for the 2 engine out, 2 green, 2 yellow, so forth, and RTLS over here. And then there's this kind of little bar right here, and what you'll see is things like ET, man, CSS, or manage and push buttons. Those actions will always be like right up here on this bar. And then we get down here into these blocks, and the blocks have a mixture of fly this way or do this. And we'll talk through some of these in just a few minutes. And then you'll see these are the things you do to get you to entry. And then when it says entry, you're over here on this little card right here. And this helps you with the pull out and the ranging to the site and that kind of thing. And then there's some steps here to help you remember how to make sure you get into the bailout autopilot. Again, these are pretty early in the program, STS-39 or so. And you can see, you know, nominal, you don't have as many regions as you do for RTLS. Why? Because the RTLS trajectory just changes so radically at so many different places. Okay. And where these were, they were actually, these are Velcro tabs on the corners, and you had all the cards kind of Velcroed together and close to each seat down near panel. C3 is where I remember them being. And then if you were looking at an MS card, it'd be just like this, but it would just say MS and it wouldn't have any color coding on it. Okay. Initially, all the stuff was manually flown. You had cue cards, flight instruments, your controllers, the rotational hand controller, translational hand controller, speed brake throttle controller, and manage and push buttons. Okay, you're all up there doing all that, and really the only thing you might do is start a dump on a software display. I remember I said everything was automated, and so once they're automated, guess what? The stuff comes up on a display. And so the 2 engine out contingencies, when we automated, they would be tracked by the software. It'd give you a region right through here, right here underneath PD3 where it has this. That's your abort region. Or actually, this is contingency abort or RTLS, and then your abort region's down here for 2 engine out, 3 engine out. Here's the yaw steering guy I was telling you about earlier. And then CIRC was it later on where I think was initially was software initiated, or the crew could initiate it with an item 6 execute. When you're manually flying it, how you got single engine roll control was you push 2 manage and push buttons for the engines that failed. Make sure you got the right ones. And then that's that single engine roll control. Okay. And then the 3 engine out contingencies, if the software saw MECO confirmed and it knew, well, we're not where we're supposed to be, then it's going to initiate a contingency abort. Kind of looks at where it is and goes from there. So contingency RTLS, artist of that, color regions. Okay. Arm and start, and that's for the 2 engine out stuff. Remember, I always said the crew always started it. 3 engine out, started on its own. And the yaw steering. Okay, so here's the flight instruments. And I've given you a graphic of the flight instruments as I knew them, which were all analog. And if you remember from the RTLS, I think it was the RTLS briefing where we talked about the abort rotary and the initial design, and here it is right here in this graphic, so that tells you how old it is. And so the major flight instruments that you would use, the very first one was the attitude directional indicator. Now, depending on how you had this selected, it had 2 modes, but essentially it was primarily pitch and roll and could be yaw. But most of the time for contingency aborts, you're flying yaw down here on the horizontal situation indicator, which is kind of like a directional gyro in an aircraft. So the 2 of the key instruments are right here. And then the other thing that we use is something called the alpha Mach indicator. This would tell you what your angle of attack was. This is your acceleration. You could read it in G's, like right now, and 30 would be 3, 4, 5, 2, so forth, so on. This would be your Mach velocity, and this is equivalent airspeed. So when it says EAS less than or something, which is a measure of Q bar, and this is what drives your separation, you would look here. And then the other guy we would use, the altitude vertical velocity tape. Now, this is showing you what we call H double dot, which is altitude rate acceleration. Really, we didn't use this for contingency aborts, but we did use this one, which is altitude rate in feet per second. And then this is our altitude, I think. Yep, just our altitude. And this is radar altimeter, and you don't need to worry about that unless you're landing. And so this would, these are the instruments you would use to pull off, if you will, your flight information. And again, you'll see where these things come in handy a bit later. So the other things that you're using in terms of your controllers, you always have to worry about where your eyebrow panel. CSS is control stick steering. That's essentially as close as you can get to manual in the orbiter. This is the pitch axis, roll, the yaw axis down here. So you're either in auto or CSS. Body flap controls and speed brake controls over here. And drag chute we're not going to need unless we're landing. Our rotational hand controller was like the stick in an aircraft for the most part. And then I don't think I called out. And essentially whether you could fly with this or not, you had to use these eyebrow panels in powered flight to give it to you. Normally, when you're in powered flight, you're in auto. In entry mode, if you're in Ops 3, you could move the stick if you were in auto, and it would take CSS automatically. But in powered flight, you always had to punch these eyebrow buttons and go to CSS first to be able to maneuver the vehicle. And so that's why I highlighted those buttons. Translational hand controller, this controlled essentially the RCS jets. If you push it up, then the orbiter's going to, jets on the bottom are going to fire. You're going to go up, down, left, right. But typically it was up to get you away from the tank. The other controller that you might use is the one over here on the right. This is the speed brake throttle controller. In powered flight, this could be used to take over manual command of your main engines. In entry, it controlled the speed brake. The way it worked, you didn't go up here and just punch manual. What you did in powered flight was you pushed this little button and you held it and you moved the lever, and you had to get within 4% of the commanded throttle setting. And once you got within 4% of the commanded throttle setting, you would see this light flip over to manual, and then at that point you had command. If you had not asked for max throttles, which was done on a software display, all the way forward on the handle would be 104%, all the way back would be 67% later in the program, 65% early. And if you had asked for max throttles, then with the handle all the way forward, you get 109. And then you'll see in contingency aborts, we often used 109 when we really needed it. And I'll talk about that in a few minutes. Just a quick look at MEDS. Mark can talk to you more than I can about this because we were just starting to get there and people were talking about the design, and I was seeing some of these displays come up. But it was the glass cockpit that the orbiter flew with for her last part of her life. And really what they did was take all those instruments that I just showed you and put them up here along with the TRAJ displays. There wasn't a lot of really extra smart stuff done, and that had to do more with the fact that we didn't want to change the orbiter computers out. And GPCs can only handle so much, and the computers in the displays can handle what the GPCs fed them. So, but yeah, it was there, and you could fly it. Okay, so here, this is the ADI that I showed you earlier in the primary flight display in the MEDS. Here's your AMI, a little bit truncated compared to the other one, but easier to read. HSI down here, you can see enough of it to be able to fly the contingency board that you need to, or the things on the contingency board that you need to. And the AVVI, which had the altitude rate and the altitude and all that right here. Okay, we already talked about the fact that the crew procedures are broken down into two main categories, and we've kind of gone through this already. 2 engine out, 3 engine out on the card, first stage and second stage. Entry procedures were common or to the flight regime, the entry cue card for each category. And so let's talk about the cards themselves. So what I've done here is we're going to look first at a set of cue cards, and this is what we started off with 39. STS-39. In this era, contingency aborts were totally manually flown. And so, and I already talked to you about the role of each particular position. The commander had the maneuvers, pilot systems management, MS2D procedure tracking, and how we color code. Here's the RTLS card. And again, this is everything's manually flown. I'm going to go back a little bit. And so let's see, I guess we'll walk through them a little later, but this gives you the idea. And what I want you to see right now is, again, everything on these cards is in action, right? This is actually roll angle. So hold your roll angle at 180, pull it 3 degrees per second. That is a rate on the vehicle. Passing alpha -10, release the RHC, hit the ET fast SEP, minus Z away. Get to alpha 30 and roll heads up so you have good roll control gains here, and we'll walk through one of those and I'll show you what that actually means with a little model I got over here. So and as you can see, the boundaries between each one, they were either mission elapsed time, an event, like this is powered pitch around for RTLS. Here's VRAIL 0 minus 30 seconds, which you could tell on the TRAJ displays. EAS 20, well, you read that off the flight instruments, and of course MECO's main engine cutoff. And again, you could read the H dot, so here EAS, VRAIL 0, so forth, so on. So you can see these are pretty easy to find things, or you either mean like the big things like PPA, well, you knew when that happened, and so you know you flipped into this regime. Again, you can see this on the flight displays, and so forth and so on. Now this card is from OI-22, and that's important because the 3 engine out are still manually flown up here. The 2 engine out are automated, and the way you can really see the difference is kind of start off looking the same, because if you look, there's actions up here right in this block. At first stage, they kind of combined everything. Check to make sure you have single engine roll control. Your failed main engine shutdown push buttons, push them. If you're above 70,000 feet, you started abort dump, abort RTLS. That's to get you into OPS6, and then put the ADI so you can read them, and then check the region. But now look what happens down here in these bottom blocks. Check theta ref 0. Check that you're rolling heads up. Check when your H dot is negative. Or when your H dot is negative, check your alpha is -4, and then you should see MECO and ET SEP, so forth and so on. So they literally do these actions, and then the vehicle flies all the rest of this. Now, the droop's a little bit different. It really wasn't automated, but it didn't need to be. And the droop was a TAL type completion or maneuver, and really it just involved you kind of taking CSS, pitching up to 60 degrees, kind of waiting a little while until you kind of scooped out from you kind of fall for a little while, and then your thrust to weight would improve, and you climb back up, and then you could actually try to complete a TAL. And I'm not going to talk about those a lot in this briefing, but I do plan, because I know Mark had suggested I do low energy TAL and high energy TALs. And so I'm going to do another briefing on low energy TAL, high energy TAL, and droop, and throw all those together into a big bag, but we're not going to talk about them much today. And then I kind of mentioned that there's this other category of aborts down here, where you have an engine out and a stuck throttle, usually stuck in the bucket's what you're really talking about. And so this says stuck first stage, and so in this case we'd follow this little lineup and we'd actually execute this procedure, and so it would fly this guy right here. But if I was later than 2 + 2.5 MET, mission elapsed time, 2 minutes 25 seconds, essentially I was going to do an RTLS. And so they would go to 109 on the remaining throttle, you go to manual, board RTLS, you're going to push the nose so it's straight up in the air, and then you're going to watch your guidance commands, and when they tell you that the vehicle should pitch around, you give it to it, and it's going to fly the rest of the RTLS. And then these over here are essentially throttle up to 109 and go fly a TAL. And that's what we call a stuck TAL. And these were times for each particular abort site. Okay. And then the entry procedures were over here. We tell you what kind of give you an idea of what alphas you were going to pitch up to, and then things that you just needed to do. Deploy the air data probes at Mach 5. Here's your Mach Alpha schedule you're going to fly. Incorporate air data, which is taking data from the air data probes and putting them in the flight control system so they do the right thing, and then the bailout autopilot if you need it. Okay. So you can kind of start seeing things shift here. And this is RTLS, same kind of deal. So really hairy stuff up here, because these are 3-engine out RTLSs, which are really usually pretty ugly. And then though actually some of these actually you probably could survive. 2-engine outs were down here. Again, actions, and then check. Here's what it's going to do. Okay. And then when they're all automated, this is what it looked like. And so yeah, it went into 3 out first, 3 out second, 3 out third. And managing push buttons is really about how to do. Put the ADIs in RAF, and then you just follow the little procedures and waited to see what it was going to do. Okay, now let's see, what is this? The RTLS contingency card. Okay, this probably isn't the best card to do a little bit of a walkthrough, because I want to go back and I'm going to show you some things. If you can, hopefully you guys, I can see my model here. See if I can make this work. So if you, for instance, and I think I can read this well enough to do it. If you're going uphill and it's between, oh, this is RTLS, isn't it? Yeah, RTLS contingency card. Okay, so if you're at the RTLS lecture, you can ignore the solids because I don't have any way of taking them off this model, but you're in fuel dissipation mode, right? And so you're up like this, you're pitched up, you're still heading this way downrange, and then all of a sudden you lose all of your engines. And so what's going to happen is telling you to stay wings level, and you're going to pull at 3 degrees per second. And what that tells you is you're pulling this way. You're pulling down at 3 degrees per second. Now, your alpha is based on where your velocity vector is, and it's down here, and it's kind of coming this way. And what you're trying to do is kind of catch it. But what you're doing is you're pitching down, and when the alpha gets to -10, which would be down here somewhere, then essentially you're going to release the RHC and step away from the tank. And hopefully it kind of goes out this way a little bit. And then what you're doing, it says, if you'll see, it says alpha 30. Well, alpha 30 is down here. And just continue to pull till you get alpha 30, and then you're going to roll heads up. And then once you get there, you start pitching. Well, I don't know if you can see that. You're down like this to get to alpha 30, and then roll heads up. and then whoop, pull up for alpha recovery, and off you go. Okay, that gives you an idea, and all I want to do is kind of show you. You have to be able to sit and read these things and really understand what's happening. And in the RTLS, it's not quite as straightforward as you might think because of where the velocity vector is and how the trajectory is changing and everything. And so most people probably would not believe that we were trying to fly these maneuvers with the orbiter. But we had the procedures in place, and if you had to do them, you had to do them because you were going to, it was your only way to survive. And again, it kind of depended on a lot of things about in terms of execution and whether you're going to make it or not, where you were when everything happened and what happened. Okay, so we've got this one. See if there's another good one here. I'll just leave this card up for a second. I think I just wanted to show you that to give you an idea of what they were. I'm not going to step through a lot of these because it'd take too long. We could be here all day talking about them.
But hey, Andy, maybe mention 3-out first stage, the drama of getting off the tank and the stack with that.
Yeah, that's a good point. I was kind of going to talk that when we got into the capability cards.
Oh, okay, I'm sorry.
Yeah, toward the end where I show you the black zones and where they were. But I know what Mark's talking about. And let's go back. I've come back to manual ones because that's what I know. Let me find the contingency card. Okay. So 3-engine out, this is the first stage. And we'll talk about this in more in detail. So let's assume the absolute worst case thing happened to you. And right after you lifted off, you lost all 3 main engines. And so there's a caveat to this, but for right now, we're going to assume you can do it. So you go ET-SEP main, and essentially this sets you up for a fast SEP later. Main engine shutdown, push buttons 3 to set MECO confirmed. And then you're in the blue region, you start your abort dump. Now, see this BFS PC less than 50. Anytime anything bad happened in first stage, 2 out or 3 out, you couldn't do anything until the solids burned out and you could get away from them. And we had no way of terminating thrust once you lit them off. Now, we talked about it, and actually it was discussed several points, but we never deemed that it was worth doing, to be honest with you. And so the pass, when it sees MECO confirmed, doesn't anymore. It doesn't care about the SRBs because it doesn't think they're there. Only the BFS can still see the sensors and tell that you're getting into SRB tail off. And so then you push the AT-SEP button, you set up for it here, and you get a fast SEP. Now, what does that mean? If I am here, when I fast SEP, I'm coming, the orbiter's coming off, and the stack is behind you, the whole stack. Solids, ET, everything. And so minus E away, and then off 602 Pro, and actually you're pulling to alpha 20 to give you some roll control gains before you try to roll heads up. And so, and again, probably in this case, you're pulling and you're inverted. You're pulling this way to get to alpha 20, and then you're rolling heads up and then coming out and then starting a pull out. And what Mark is referring to is whether or not you would have even held the stack together. Whoops, well, that's not good. I just broke my stack, but I'll fix it later. There's a lot of debate about that, and a lot of skepticism that because of the aerodynamic loads that would exist, that the orbiter, one of 2 things would happen. The first one was that the aft struts would load up and break, and they would not withstand the aerodynamic loading. We actually did solve that later. But the other piece of it was there was a lot of uncertainty with the loads that you had, even close to SRB SEP, whether or not you would get away from the stack, and it's the stack, not just the tank, cleanly. Um, but again, you don't have any other options, so that's what you had to do. When the interesting thing, and I'll tell you a fun story about this, one of the things that John Young loved to try to do was 3 engines out off the pad and then see if he could do a split S and land the orbiter at the skid strip, which was close to the launch site. And John could actually pull it off. Now, the simulator doesn't really know whether the vehicle is going to hold together or not. But as far as the simulator was concerned, you could separate from the tank and you could fly it. And it literally was a split S type maneuver to get to the skid strip. The funny thing was that John was about the only guy that could consistently pull it off. And none of the other guys, and I won't tell you who in particular, but one of the astronauts in particular was working with him on this stuff and kept trying over and over and over, never could quite get there. So we were looking at all that kind of stuff, trying to improve survivability. And actually late, I don't remember exactly what year it was, there was some work on the orbiter going on, and they actually discovered that they could beef up the aft struts, and it wouldn't take very much to get it to withstand the actual loading, the aerodynamic loading that was expected for a 3-engine out case, and they went ahead and did it. Now, there's still a lot of uncertainties, and people, and as I'll show you in the capability charts, they still considered that a black zone. I don't consider it, I personally don't consider it an absolute, but I'm not sure you can really talk about very many of these things in terms of absolutes. Just kind of best effort for most of this stuff. Any other questions or anything else you want to talk about?
Well, I'm not sure if you're going there or not. If you're not, one thing I've noticed when people ask me about contingency aborts, they usually have a quote, and I can tell from the quote that they're talking about a time frame of the program. The distinction I would make is going into through STS-4, the goal of contingencies was all about being able to eject. There wasn't much effort for runways.
Right.
Then prior to Challenger, it was all about ditching. Then after Challenger, it was about bailout. And then my question for you, because I got there at OI 26.
Yeah.
When did the program realistically start aiming for the East Coast?
Mostly, well, if I remember correctly, I think what happened was we actually started flying 2-engine outs to Bermuda first. And where it really became important for 2-engine out up the East Coast was when we started talking about going to ISS. And so that, we weren't doing, I was trying to remember how much of that we were doing. I remember it, really coming into play then. And so it really was a result of flying 51.6 degree inclinations, to ISS. And that's when all the East Coast stuff started happening, and really started doing a lot of work on trying to expand that capability, which there was always something going on, and 9 times out of 10, John was the one pushing that stuff.
Yeah,
to expand the envelope. Any other questions there? Yeah, I kind of touched on some of that, but that's a good question.
It's kind of. I'm sorry, it's Philip. I think it's kind of the kind of segueing from Mark and maybe segueing into the capabilities that you're going to talk about, because that's what I was always wondering about at the end of the program when you're flying 51.6 pretty much on every mission is, how it affects your ability to you're closer to the coast, how much it narrows your black zones, if at all, how in these contingency cases, like is there any possibility of making with a 3-engine out case, being able to make it, limp into South Carolina or something like that, on low energy?
The easiest way to answer that question is to jump ahead. I was going to do a walkthrough here, but we've kind of walked through a couple of them, and I'm going to skip on over because your question is, did we have 3-engine out capability? And we did, and you can see that. Now again, this is from a velocity standpoint. This is pretty late in the program. I don't know exactly when this, oh, it's 114, not that late. But this is an eCal procedure. And again, most of this is all automated, so it's checked most everything. There is an action right here. Notice here it says pull up to alpha 58 at 4 degrees per second, go back to auto just to help it get nose high. But if you look at this chart right here, this is showing, when you see these numbers here, these are velocity numbers in inertial velocity, which is pretty much how you talk about things once you're in second stage. And so, and the window that you would have to each particular East Coast site was not only a function of velocity, but where you were in the launch window. And I know Mark talked a little bit about this a couple of weeks ago on Facebook, but the window would open about 2 minutes 30 seconds before the actual in-plane time. You are kind of furthest away from the East Coast if you launch at that point. The middle of the window is here at the in-plane, and these are the numbers for 2 engine out and 3 engine out. And then the best capability is going to be over here at in-plane plus 230, because essentially everything's moving to the west, and so are you. And so you're still flying 51.6, but you're just a little bit closer. So the windows, actually in in-plane looked a little better here. A little bit here you can see Wallops, for instance, is a little bit bigger. Atlantic City's a little bit bigger, and so forth and so on. And let's see if it shows up over here. No, not quite so much. They're pretty static. You don't see as big a shift with in-plane, but you can see some right here from in-plane to in-plane plus 230, for instance. You get another 600 feet per second to go to Kabreski, and so forth and so on. So yeah, there was capability, and these charts here kind of show you what kind of windows you had. And again, crew in the ground would track it as they went through, and if they had to do a 2 engine out or 3 engine out, they might actually try to get here. When this would be, I don't remember when we were working it early, we did not worry about 3 engine out. So this is, I'm pretty sure, a result of the 3 engine out automation. Was all this expansion. We were up here. Generally for a 3 engine out case, I'm not sure we did very much looking at this. I don't remember even having a really good procedure to fly. But again, I left my job doing this stuff in '94, so you know, we were kind of some of this stuff wasn't completely automated yet. We had talked about it. I knew it was coming, and so forth. And I knew how it was going to work, but that was about it. Any other questions? And again, you know, we kind of we got even the program. I mean, when we started talking TAL delay, I wasn't sure what kind of resistance we were going to run into with that one. That was, again, John pushing on this and wanting to keep the vehicle as close to the coast so you could do a 2 engine out landing if you needed it. And of course, there's a debate, because what you're really doing is you're deciding that if you have an engine out, it's probably, or second engine out, it's going to be early. It's not going to be late. If it's late, then you'd rather be already heading out across the ocean so you can complete the TAL. So there's a bit of a trade, but the program actually did buy off into staying closer to the coast and to pull off a landing if needed. And so we had the TAL delay procedure that helped us with that. You have to, for you to survive these cases, the engines had to shut down without blowing up, and hopefully benignly. And you also had to get flight control to recognize that you were 2 or 3 engine out for a lot of different reasons as quickly as possible. So again, having limits inhibited actually works against you for most of those cases. So does that clarify things for you about that relationship?
Yeah, I was mainly interested because 51F flew with limits inhibited during that abort case.
There are parts of it, but that was a different scenario, because that first engine out was not caused by a real engine problem. It was caused by a sensor failure and actually some other issues. But the sensors took it out. The engine itself actually was healthy. The problem was that those sensors were extremely reliable, and the flight controller, who was Jenny Howard, realized that she actually enabled limits for a little while, and then she saw another engine that was headed to the same failure mode as the one that had gone down, and she made the correct call. She realized that the sensors were going to take that engine out, and so she called for limits to inhibit to keep that from happening, and we got a safe shutdown, at the right time, essentially a small underspeed, I think. But so that was kind of a different scenario. And then those sensors were improved so that we really didn't have to worry about that particular issue anymore. So Jenny actually probably saved the vehicle, even though I think I read Tommy Holloway. I've got some either newspaper or something where they kind of patted her on the back for it. I always thought she should have gotten more recognition than she did for making the call she did. But that's my personal opinion.
Okay, understood. Thank you.
Hey, and I'd add, Andy, I don't know when in the program, because I think it was after I was there, the limit switch looked at 5 basic parameters.
Right.
At the end of the program, they got it down to 4. So they
Oh, is that
decided one of those parameters didn't matter, apparently. From
Yeah,
that perspective.
and we were working AHMS, Advanced Health Monitoring System, at the end, in addition to the red lines where you were monitoring engine vibrational modes. And because those could often key you that something was about to happen on a bad day. And so we had just kind of barely started flying with that system, I think, toward the end of the program, which was even better reliability in terms of getting the engine shut down safely. Okay, any other questions? So these are the cue cards. This is the entry alpha card, and on the left, and that shows you essentially what alpha you should be flying, at what Mach number, and what range you should be at, and what altitude you should be at. And from this, the crew can tell what their energy state is, whether high or low energy. Bailout cards on the right. Essentially, these are all the procedures you'd go through. And like I said, I may do a little short briefing on this one at some point. I'm going to do the TAL stuff next at some point, another couple of weeks. Here's contingency card. I'm not sure what I'm trying to show with this one. It's an RTLS contingency card. Now here's the capability cards, and so if you look at this at 51L, at least according to this analysis, they considered, and this is kind of a generic. These are all kind of generic cards. They're not mission specific, and it could vary from mission to mission, and it did vary from mission to mission. But you can see we had large areas where they really didn't think you were going to get the orbiter to even to a good ditching, and there was no bailout capability to speak of, and that's what you take away from this one. Very little runway capability, and of course a single engine TAL, if you lose a second engine, well, you're going to get there anyway. A-wave, shallow wave, kind of expected that one. H-dot plus 100 is actually a point where you can complete an RTLS almost doing nothing. And so these 3 areas are not a surprise at all. And then by 91, we'd improved things quite a bit. We had bailout capability for most of it. Again, here's the 3 engine out. Notice that they show a little area right here where you have bailout capability. So what that really says to you is if you can get through this region and the orbiter still on the stack, you're probably going to be okay, and you're going to be able to pull it off. If the orbiter comes apart back here, the stack comes apart, and all bets are off. And then this was usually a bad region, 3 engine out between 10 and about 13K. Just the pullouts and everything were very high G, very high Q bar. RTLS right around par pitch around to VRAIL 0. Some bad areas for 3 out. 2 out, most of the time, they could still be ugly, but probably survivable. Let's see, this looks a little better. We got ECAL here on these, and actually up here by 91. Bermuda, like I said, I think we started flying Bermuda first and then ECALs later. And Bermuda is where the technique was essentially invented. The future capability, I think we got pretty close to this, but I actually don't think it got quite this good. It was pretty close, but again, but what you can take away from all this is you can see we continuously improved it, to the point where even if we lost an orbiter, we probably weren't going to lose a crew. And actually, not only from an asset standpoint, but as a safety guy working the end of the program, that's where I would say we were in general with flying orbiters. It's like we think we've got enough mitigations and safety improvements where we can't say for sure because we never did get the tank foam problem totally tied down that we won't lose another orbiter, but we're pretty certain we wouldn't lose another crew. We had other things we could do to get them home. Okay, so this is a 51.6 degree chart for contingency abort capability. And that's all I've got on this briefing. Do you guys have any questions? So like drinking with a fire hose?
Hey, Andy, on the eCal aborts, what
Yeah.
was the guidance? Was it TACAN or GPS or radar or what?
It depended on when you were talking. Initially, it was TACAN early in the program, and then once we put GPS in the vehicle, it was always used if it was good. You'd have radar tracking for powered flight. Actually, I don't know that we had much once we got on the entry side. I don't think we did. We had some, but again, it kind of depended on when you were talking the program. If once we had GPS available to us when we got it in the system, we're going to use it, and we did. And actually, there were a lot of arguments when we got GPS in the system about lowering. Well, we didn't protect weather constraints for these, but obviously the GPS gave you such good accuracy, you might, instead of picking a bailout on a particular day, you might actually take a chance at landing even if the weather's really crappy. So that was kind of part of the difference that would make versus trying to fly a TACAN into a landing. It's like you don't have the precision that you really need. So you might, even if you didn't think you could make a safe landing based on the weather conditions you had, you might choose to bail out anyway. But you just do it as close to the shore as you can so people aren't in the water very long.
Okay, understood. Thank you.
Okay. Anything else, guys?
Andy, I wouldn't mind your perspective from pre-Challenger to RTF. What I seemed to notice, since I wasn't in the program at that time, in the documentation, that prior to that, the philosophy was to, for a contingency was to try and ditch, but nobody, at least privately, thought that that was survivable.
Right.
Documentation didn't explicitly say that till after Challenger. And I was just wondering how the crew office generally thought of ditching. I assume they thought it was a waste of time, but
Well,
maybe.
I wouldn't call it a waste of time, but I would agree with you that we had serious doubts about whether that was survivable. And again, for the different reasons, with the payloads in the vehicle and all that, and then you blow those upper windows out and blow the side hatch off and have a shot at getting out. But like I said, water impacts at over 150 are going to be bad, and of course the orbiter would have hit them at about 200, and so that would have been just a really, really, really bad day. I don't think any of us really thought that a ditching was going to be survivable. But again,
I was just always confused that the documentation didn't explicitly say it until they were forced to say it, I guess, after Challenger with RTF.
Yeah, that's probably a valid assessment. I mean, again, these things were not formally supported. They were best effort based on a lot of people wanting to do what they could to get the crews home, and that's just kind of where it was. And so, yeah, I would agree with that assessment. I think that's accurate. Any other questions? Okay, well, thank you for coming. I appreciate your time. You know where I live if you do have any more questions. I am going to work on a TAL droop and high and low energy, and that'll probably take me a couple of weeks. The bailout thing just occurred to me today, so I'm not sure when I'm going to get to that. But I am recording this, so I'm going to put it in two pieces probably and put it up on my YouTube channel. The Ascent one that I think some of you may have been at, but a lot of you may not have been. But anyway, there's a nominal Ascent one that'll go up on the YouTube channel, and then again I'll do that. I'll put out a notice in the groups like I have been doing when I get the Tau one where I'm happy with it and feel like it's worth everybody's time. So anyway, if you don't have anything else, I appreciate you coming. Hope you enjoyed it. Hope you learned something. And we'll see you later.
Thanks a lot.